A. I need a non-deterministic finite automaton that accepts precisely the language consisting of the empty word. And I need another non-deterministic finite automaton that accepts nothing. So, let's start with the first one, the language consisting of the letter A. What would you suggest? As I said, I need an NFA that accepts precisely the letter A and rejects everything else. And so, in order to get to that, what kind of automaton will I have? Well, this is actually not that complicated. Let me first draw the diagram, and then we will do the enhanced transition table, because that's really how we're going to work in the construction. But the diagram is obviously very simple. We have an initial state. Every finite automaton, be it deterministic or non-deterministic, has to have an initial state. And so we have that initial state. And from that initial state, there's a transition under A, and it goes to a final state. And that is the automaton that we need, because it will, as you can easily see, accept precisely the letter A and nothing else. Now, it is necessarily a non-deterministic finite automaton, regardless of what the alphabet A is, because from that final state there are no transitions. Therefore, it is not deterministic. And so if we call this Q0 and we call that Q1, then we will have this automaton. I'm sorry, Q0 and Q1. And now we have a letter A, and then we have all letters B other than A. So I'm going to do that somewhat schematically, because obviously the alphabet may have other letters. It may be A, B, C, D, E. So for A, it would do something, and for B, C, D, it would do something else. And so if we look at this automaton, then from Q0 under A, we obviously go to Q1. And under B, other than that A, we don't go anywhere. And then from Q1 under A, we don't go anywhere. And from Q1 under any other letter, we don't go anywhere. And the initial state is Q0. And we have exactly one final state, which is Q1. And so this is then the definition of the non-deterministic finite automaton that accepts precisely the letter 1. And therefore, what we have here now is a non-deterministic finite automaton for one of those three basis elements. And of course, if it were B, then we would have the column for B and the other column not anything other than B, and so on and so forth.
Professor,
okay. Yes?
Why is Q1 accepted and Q0
Q1 is accepting because we have to accept the letter A.
So it accepted the letter A from Q0 to Q1.
Yes.
And that's why it's accepting?
No, it is accepted because there's a transition from the initial state to Q1, and Q1 is accepting.
Okay.
So we have a path that describes that corresponds to the letter A, which goes from an initial state, the initial state, to a final state. In this case, there's of course a single final state, and that's why the letter A is accepted, but nothing else is. Does that clarify it?
Yes.
Okay. Any other questions? So the next thing, so we've got a NFA for that. Now we need an NFA for that language consisting just of the empty word. Well, this is getting increasingly more complicated. There is your Q0. It is the initial state, and that will be it. If we apply epsilon to the initial state Q0, then obviously we go to Q0, we stay in Q0. Q0 is a final state, and therefore epsilon is accepted. If we have any other thing, any letter, A, B, C, D, E, then that would get us to, we will basically fall off the state, and so clearly that is rejected. So the corresponding enhanced transition table is then all letters in A. We don't go anywhere, but the state is accepting. And finally, the most difficult one. We don't want to accept anything, so we have an initial state that happens to be rejecting, and so we have the same thing as before for the language consisting of the empty word, except now that state is rejecting. So that means we now have non-deterministic finite automata for each of those three basis elements, and that will take care of the basis. So what that means then is that we can construct an automaton for this A. We can construct an automaton for this B. We can construct another automaton for this second B, and another automaton for that second A. So we will basically construct 4 automata, one for each of those letters, and then we'll have to combine them, so there are a number of technical conditions that have to be satisfied. But basically, we have now a starting point for our construction, which of course mimics exactly the way we verify that this thing actually is a regular expression. We go with the basis elements, and that means we have A, B, B, A. These are basis elements, and then we apply the one of the 3 constructions, concatenation, union, or star, and that then allows us to carry this out, crank this out systematically. So the basis we've dealt with. Now we have to do the construction. We will do first the union construction, then the concatenation construction, and then the star construction. Now, in order to do that, let's do the union. We will have to make an assumption. Now, if you go back to the definition of a regular expression, which I wrote down last time, but you can go back and consult it. But basically, it says that if we have a regular expression, if we have 2 regular expressions, for instance, A, B, and B star, then the union of those 2 regular expressions is again a regular expression. Now, if we consider that, then basically we want to have a regular expression alpha and a regular expression beta, and that union of those 2. Now, what we need then is, by assumption, this is the inductive assumption, that we have actually somehow mysteriously, this is of course the usual trick that one can use when one does recursive arguments, we assume inductively that there is a non-deterministic finite automaton for this alpha. Somehow we got that. And we also have a non-deterministic finite automaton for beta. Somehow we got that. That's, of course, the beauty of inductive constructions. You have a basis, and then you have the inductive steps, in this case 3, one for the union, one for the concatenation, and one for the star. And once you have completely specified those 3 inductive steps, you basically have a mechanism for constructing a non-deterministic finite automaton for any regular expression. So what we need then is we assume we have these 2 non-deterministic finite automata, and then we want to construct a union automaton, an automaton that corresponds to the union, which of course means it has to accept that union automaton has to accept everything that in alpha accepts as well as everything that in beta accepts. Because by assumption we assume, by induction we assume that the language denoted by alpha is exactly the language accepted by n sub alpha, and the language denoted by beta is exactly the language accepted by n sub beta. Now we have to write down those 2 automata, and we will actually do that in general for all 3, because we will do the same thing for concatenation and for star. Star, of course, requires only 1 automaton. Concatenation requires 2 as well, n sub alpha and n sub beta. And so we're going to assume we have n sub alpha and we have n sub beta. And these, of course, are quintuples, both of them. And now we write down as much as we can, and then we'll have to specify what else is missing for the union automaton. N1 is the union automaton. So n sub alpha obviously has an alpha bit, and in fact we can clearly assume that both non-deterministic finite automata have the same alpha bit, because a regular expression is over a fixed alpha bit, and therefore that alpha bit is always going to be the same. And then we have a set of states, let's call it q sub alpha for n sub alpha, and a set of states q sub beta for n sub beta. Now there is a little bit of a sleight of hand that, well, no, let's go first tau alpha and tau beta. These are the 2 transition functions. And now the sleight of hand is that we always use q sub 0 to denote the initial state. That may look a little complicated initially, but it actually makes the whole definition much easier, the formulation of the constructions. So we have q sub 0 as the universal initial state, and then we have 2 sets of final states, f sub alpha and f sub beta. So we are given those 2, these are given. With that property, that the language denoted by the regular expression alpha is exactly the language accepted by n sub alpha. The language denoted by the regular expression beta is exactly the language accepted by the non-deterministic finite automaton n sub beta. And now we want to construct the union. So let me draw a simple diagram. So there is n sub alpha. And there is n sub beta. So intuitively, and there are transitions and whatever, these are diagrams, the usual whatever we do with when we draw a diagram for a non-deterministic finite automaton, transitions leaving the states and so on and so forth. So what do we have to do in order to get an automaton that accepts everything n sub alpha accepts and everything that n sub beta accepts, but nothing else? So if you think about it, what if we were to take those two initial states and make them one? So whatever transition we have from this will also be from that, and whatever transition we have from this will also be from that. Well, think about it. What would this new automaton that I obtain by identifying these two initial states as the initial state of that union automaton, well, what will it accept? It will accept everything that n sub alpha accepts, because it contains that initial state, and then whatever there is, whatever path there is to a final state is going to be a path in that new union automaton. And the same holds for the second automaton, n sub beta, because we can start in that new initial state, and we can take the transitions that take us into n sub beta. Now, there are some technical issues that we will have to look at. One of the things we want to avoid is that somehow we can go back to the initial state of an automaton. So what we need to stipulate is a property that is non-returning. Non-returning to the initial state. That looks complicated, but you can completely ignore it, because the construction is such that if you have a non-deterministic finite automaton with that property, and you apply any of the three constructions, union, concatenation, or star, you will again get an automaton, an NFA, with that property. So since all three basis automata are non-returning, there is no transition that goes back to the initial state. Once you've left the initial state, you can never go back with any of the basis automata. And we can then verify, and that goes tacitly, it's a freebie, you don't have to do anything, it just happens, that the union construction, the concatenation construction, and the star construction have the property that if you apply them to a non-returning automaton, one that does not have a transition back to the initial state, you will again get a non-returning automaton, one that doesn't ever go back to the initial state. So you actually never have to worry about this property. So if you don't like to think about it, ignore it. But it is an important aspect because the constructions that I'm going to give you for union, concatenation, and star actually can be applied to any non-deterministic finite automata as long as they have certain properties. And the properties are relatively mild. They have to be non-returning. And the only other thing is that Q sub alpha and Q sub beta have as little in common as possible. Now, we would be interested in saying that they are actually, the intersection is empty, but we can't do that because it is immediately contradicted by the presence of Q0 as the initial state for both of them. So that simply means then that the only thing these two sets of states have in common is that initial state Q0, which is not going to be a problem because the automata are non-returning. So once you've left the initial state, you can never go back to it. And so if the two automata actually have the initial state in common, there's not a whole lot of harm done.
Professor, could you tell
Yes.
us again can you tell us again what Q does? Capital Q alpha or
Capital Q is the set of states. So N Q sub alpha is the set of states of the automaton N sub alpha. Q sub beta is the set of states for the non-deterministic finite automaton N sub beta.
So in this situation, you're saying, back to what we were talking about just a moment ago, that Q's of alpha does not intersect with Q's of beta, and then that's what
Except for having that initial state in common.
So if we look for just the initial state, and then after that,
Nothing else.
Nothing
Correct.
Similar. Okay.
That simply, look, from the drawing here, I obviously am assuming that. If I were to have some states in common in N sub alpha and N sub beta, I might end up with something like this. Obviously, that doesn't make any sense that there are states in common. So we don't really think about that, but mathematically we have to state that because otherwise somebody may in fact come up with some crazy thing like that. And that obviously would screw up everything. So we don't really want that. But the intuitive idea is that we have here an automaton, and here's another automaton, and basically they have nothing in common other than the initial state now. Okay? So, that means now we actually want to define N1. N1 is the union automaton, and of course it has to have certain things. It has to have an alphabet. Well, that alphabet can be nothing. There's nothing to be gained by changing the alphabet. So this is again the same alphabet. We have a set of states Q1. We have a transition function Q1 at tau 1. We have Q0 as the initial state because every initial state is called Q0. And so this one is also called Q0, and we have F1. So effectively, in order to define that union automaton, we really have to define just three things. We have to define Q1, we have to define tau 1, and we have to define F1. So what, given this drawing, which informs basically the construction that we're carrying out. What would you suggest should be Q1?
Union of alpha and beta, the initial state.
Of Q alpha and Q beta. All right, let's write that down, but let's think about that before we actually accept that. So Q alpha union Q beta. Now, looking at this drawing, obviously what we want is that every state that was in N sub alpha is in N1, and every state that was in N sub beta is in N1. Now, the only complication is, of course, that if N alpha has M states and N beta has N states, if this were the definition of the states of N1, how many states will N1 have?
Can you repeat the question?
The question is, if the first, the N alpha has M states, and the N beta has N states, and we're using this definition of Q1, which is the set of states for N1, the union construction, that overall thing. How many states does N1 have? How many elements are there in Q1?
M plus N?
No.
Whichever's larger, M or N?
No. Don't guess. The obvious thing is M plus N, but that ignores the fact that they have one element in common.
Oh, M plus N minus 1.
M plus N minus 1. Exactly. All right. Now, I obviously expected everybody to think M plus N because that is what you would think. But that's why I'm pointing it out. It actually is one less than that because of the fact that both initial states are in Q1, but of course there is only one that will be counted. And so that merger of the two initial states of the two original automata is going to result in the fact that this new automaton has M plus N minus 1 states. So that is the definition of Q1. And now let's go straight to the set of final states. Well, what do I want to be a final state in that union automaton? Well, obviously, I want everything that was a final state in either N sub alpha or N sub beta. Because when is a word accepted? Well, if there's a path from the initial state to a final state, and since we want to be able to accept everything that was accepted by the first automaton, N sub alpha, as well as everything that was accepted by the second automaton, N sub beta, we obviously, since we have basically merged the initial states of the original automata N sub alpha and N sub beta into one new initial state, we then want to have a path from that new initial state to any final state that was either in N sub alpha or N sub beta, which means we have F sub alpha union F sub beta.
The reason that you fuse the two initial states, could you explain that again? Is it just because we only ever have a single start state?
Correct.
Okay.
That's what it is. And of course, we want that single initial state to allow us to initiate paths that either end up in a final state of n sub alpha or a final state of n sub beta. But once we've decided we're going to go, say, into n sub alpha, we never can go somewhere over to n sub beta because these are non-returning automata. So once we've made a decision, we're going to go left from the new initial state or right from the new initial state. We're going to be stuck with that decision. So once we've gone left, we will stay left. Once we've gone right, we will stay right. There is no way of going back. And so that means we have defined two of the three things. So the only thing that's left is to find tau 1 of Q and A, where Q is a state of the new set of states, Q1, and little a is a letter from the alphabet. And so in looking at this drawing, where is anything interesting actually going to happen? Well, if we are in a state in n sub alpha, then we're simply going to do whatever we did before. And if we're in a state in n sub beta, we're simply going to do whatever we did before. So the transition function for either of these two states is going to be the same that it was before in the old automata. The only state that does anything new in the union construction is the initial state. In the initial state, we want to be able to initiate paths that go into n sub alpha or that go into n sub beta. And how do we do that? Well, we take the transition function of n sub alpha for the initial state, and we union that together with the transition function for n sub beta in the initial state. So if Q, this Q, is Q sub 0, then we're going to do tau alpha of Q sub 0 and A, union tau beta of Q sub 0 and A. So that means that if there are a bunch of things that we can get with A from that initial state, we're going to have that in the first automaton, and then we may have a bunch of other things in the second automaton under A, and we're going to take all those plus all those. So this is tau sub alpha of Q sub 0 and A. So this is obviously the old Q sub 0 of this is the old initial state of n sub alpha. And we do it under A. And then we do the same thing for the initial state of the second automaton n sub beta, which of course is given by tau sub beta of Q sub 0 and A. And that is if Q is Q sub 0. That's the only time when something interesting is happening. The only other cases that we have to consider is that if Q is a non-initial state of the first automaton, or if Q is a non-initial state of the second automaton. We've already covered the case where that Q is Q sub 0, the new initial state. And now we have to talk about what happens if that Q is a state in the first automaton other than Q0, or a state in the second automaton other than Q0. And in this case, it is completely boring, because if the state is a state of the second automaton, then it is tau alpha of Q and A. And if it is in the second automaton, then it is tau beta of Q and A. So nothing changes. We do whatever we did before. And that finishes the definition of N1, because we've defined the three things that we didn't know: Q1, F1, and tau 1. So that is the union construction. Now we get to the concatenation. So we have alpha concatenated with beta. We, as before, we have n sub alpha for alpha and n sub beta for beta. And we are assuming the same. This holds for all automata. So n sub alpha is given that way: a q alpha, tau alpha, q0, f alpha, and n sub beta. A q beta, tau beta, q0, f sub beta. And they're non-returning, and the intersection of the two sets of final of states contains only the initial state and nothing else. So this is not just for union, this is for concatenation and star as well. And so we now need an automaton, call it N2, that accepts the concatenation. So we want to get everything, so that N2 should accept precisely all the words that can be obtained by taking a word from the first automaton, n sub alpha, and concatenating it with a word from the second automaton, n sub beta. And so, again, obviously we have an alphabet, we have a set of states, we have a transition function. Q sub 0 is our universal initial state, and we have F2. So again, there are three things that need to be specified. And so let's see how we're going to do this. Now, there is my first automaton in alpha, and there's my second automaton in beta. Now, if I have a word, so if I have a word W in here, then obviously it has to be concatenation of, now let's do U and V. U concatenated with V, and U has to be in here, and V has to be in here. Now, what does that mean? It means for U to be accepted by the automaton n sub alpha, there has to be a path from the initial state to a final state. So the U ends up there. If it doesn't, if we can't find a path from the initial state to a final state, then obviously that word wouldn't be in the language accepted by the first automaton. And now the V is doing the same thing. So it has to end up in some final state from the initial state of the second automaton. And so now the $64,000 question is, how do we actually link these up? Before, in the union construction, that actually was easy, because we simply merged the two initial states into one new initial state, and that did the trick. Now it's a little bit more complicated. Basically, we have some transitions. So there may be some A's. And remember, these are non-deterministic finite automata, so there could be several transitions from the initial state under A.
Professor, I don't really understand how we're doing, what exactly is going on with these pictures. So, like, the concatenation is saying that we start off at the initial state and then we're going to go all the way down to...
Well, no. I haven't really explained yet how we concatenate. All I have said is that if we have a letter U in, a word U in L of n sub alpha, then that means there has to be a path from the initial state to some final state in the first automaton in n sub alpha. And if there is a V in the second automaton, accepted by the second automaton, that means there has to be a path from the initial state to some final state of the second automaton. Okay? I haven't gone any further than that. So this is the same thing that we did here, except we wanted to get both paths captured. If there is a path from the initial state of the first automaton to some final state, we want to be able to do that path. If there's a path from the initial state of the second automaton to a final state, we want to be able to capture that path in the union construction for that new automaton in 1. Now, from concatenation, this is quite a bit more complicated, because now we have to be able to jump from that final state. After all, this is where the U ends. This is the U that we're using. How do we get over to the second automaton? And what we're going to do is we're basically adding to the transitions. And there may be a number of transitions that leave this final state. And now we are adding, we're not replacing, we're adding all the transitions that we have from the initial state of the second automaton. Because that allows us to start this word V, which presumably starts with the letter A, according to this. So it goes into the second automaton non-deterministically. There may be other transitions in the old automaton under A, and we're not going to change that. So non-deterministically, one can decide whether one stays in the first automaton or transitions over to the second automaton. And that way we can go over to that second automaton non-deterministically. We're not forced to take an A if we want instead to take the little a and stay in the first automaton. That's perfectly okay. It's a non-deterministic finite automaton. So there may be several transitions under A. But if we decide that we consider this final state to be the state that accepts U, then we can concatenate with something else because U is in the language accepted by the first automaton, n sub alpha. And so doing this, it then allows us to make that jump from the first automaton n sub alpha to the second automaton n sub beta, because obviously if we want to get this word accepted in that new automaton n2, then that means we first have to accept U in the first automaton n sub alpha, and then V in the second automaton n sub beta. And so it has to end up in a final state of the second automaton in order to be the concatenation of these two words. Now, if there is a state that is rejecting in the first automaton, then we obviously don't add these, because we will be allowed to do that jump over to the second automaton only if we ended up in a final state, only if that word that got us to the state is accepted. And so what we then get is this new automaton. The first little glitch here is, of course, that once we do this construction, and of course we have to do that for all final states in the first automaton, that will result in an automaton in which that initial state of the second automaton does not really occur anymore. Well, it occurs, but we're going to suppress it, if you will, because you can't get to it. Remember, by assumption, these are non-returning, so you can't get back to the initial state of the second automaton. And because we are bypassing the initial state, we're going to where we have transitions from the initial state to these states. We're bypassing the initial state, and that means that we can't really get to that initial state of the second automaton, and therefore we can essentially make it disappear. So what that means is we now have to define Q2, F2, and tau2. What do you suggest should be the states of that new concatenation automaton?
You're asking for the initial state?
No, I'm asking what should be Q2? What should be the states? What should be all the states of that new automaton N2 that is supposed to accept the concatenation of the language accepted by the first automaton N sub alpha and the second automaton N sub beta?
I'm sorry, could you rephrase that? I'm having a hard time understanding your grammar.
I am asking, what is Q2? What are the states of the concatenation construction automaton?
Would it be all states in the first one and then the second one minus one?
Right. Basically, what you want, if you look at the drawing, the schematics, you want all the states of the first automaton, and of course the initial state of the first automaton should then really intuitively be the initial state of the new automaton N2. And then you want all the states except the initial state of the second automaton. Now, the trick here is, of course, that we're using Q0 as the universal initial state. So effectively, if we take Q alpha union Q beta, then we are really not looking at that initial state of the second automaton at all, because this, as I said, if we have M states here and N states here, then that will have M plus N minus 1. And so this is M plus N minus 1, N minus the initial state. And so this actually works beautifully because we're using this trick that the initial state is always Q0. So effectively, we make that initial state of the second automaton disappear because it doesn't really figure in anything. So it is indeed Q alpha union Q beta, but effectively the interpretation is that we take all the states of the first automaton, Q alpha, and all the non-initial states of the second automaton, which is Q beta minus Q0, but we don't have to write that down because the Q0 disappears anyway, because we have Q0 and Q alpha, and therefore the Q0 and beta disappears because it's the union. Q0 occurs only once. Okay?
Wait, Professor, I have a question.
Yes?
Okay, so just could you give us an example of like of a word that where this is happening on, so that we can have a better example? Because I'm looking at Q1 being U, and then that one is, you can get all the states from there and add the states from B minus 1 being the initial state. Does that mean that if you're concatenating, you grab the whole word and then you add another letter or something in the middle or at the end or whatever?
No, the
it is?
V will presumably start with a letter. So the letter would be A, which gets you from the initial state and the second automaton to some state. And so instead of doing that, we're adding all the transitions from the initial state to all the final states in the first automaton. That allows us to pretend that each final state of the first automaton is also acting as an initial state of the second automaton.
So that means that in every state in
every
U,
final state.
in every final state in U, you can actually begin a V.
Correct.
So
Precisely.
meaning
That is the whole idea.
So any letter, I'm just considering in language terms, any letter can be an initial state for another letter in V.
Yeah, well, sort of. You're mixing things, but intuitively, yes. Okay? Now, there are, of course, a few complications. The first complication, which is the main complication, is that this V could be epsilon. If the V is not epsilon, then it should be fairly obvious that everybody who is in the concatenation must end up in a final state of the second automaton. Because that's where we have to end up. I mean, we're not doing U, we're doing U concatenated with V. So if the V can't be epsilon, it has to have at least one letter, and that means we actually have to do some transition in the second automaton. And that means that whatever is accepted, that V has to be accepted, and it has to be accepted in a final state of the second automaton. Because, as I said, we're treating every final state of the first automaton as an initial state of the second automaton. And so if V is not epsilon, then we actually have to go over there and end up in a final state of the second automaton with that V. If we don't end up in a final state, the V is not accepted, and therefore this is not a valid thing, because the V has to be a word in that second language, L of n sub beta. So that has a number of implications. We have to think about what happens when we have an epsilon in that second language, and what if we don't. If epsilon is not in that language, what does that mean? Well, in particular, it means that the initial state is rejecting. You see, the whole idea of the non-returning property is that the initial state will determine only the fate of epsilon, whether it is accepted or not. Everything else has to go somewhere else in order to be either accepted or rejected. But the empty word, whether the empty word is accepted by the automaton, is exclusively determined by the initial state, and only that word is determined by the initial state. So whether a word is, if we have a word that is not epsilon, the initial state has nothing to do with that. So the only word that is, whose fate is decided by the initial state, is epsilon. And so if the initial state is accepting, then epsilon is accepted by that automaton. And if the initial state is rejecting, then epsilon is rejected by that automaton. And so if this second language does not contain epsilon, then all words that are composed of a word from the first language and a word from the second language, and concatenation of that, must end up in a final state in the second automaton. And so that then informs the definition of F2, because we basically have to distinguish what will happen if we have Q sub 0 in F beta or not. Q sub 0 in F beta simply is the same as asking, is the initial state of the second automaton accepting? If Q sub 0 is in F beta, then the initial state of the second automaton is accepting. If Q sub 0 is not in F beta, then the initial state of the second automaton is rejecting. So if Q0 is not in F beta, if the initial state of the second automaton is not accepting, then epsilon is not in the language accepted by the second automaton. And in that case, we actually have to end up in a final state of the second automaton, and that simply means that F2 has to be equal to F beta. We must go, well, we obviously go to some final state in the first automaton with U, and then we transition over to the second automaton with the first letter of V, and then we eventually have to end up in a final state in the second automaton. Now, if Q sub 0 is in F sub beta, that means the initial state of the second automaton is accepting, and that, of course, means that epsilon is accepted by that second automaton, that V could be epsilon. And if the V is epsilon, then we could stop in the first automaton in a final state. Because if V is epsilon, then any word that is accepted by the first automaton in sub alpha is in fact in the concatenation, because the V could be epsilon, so we just have U, a word from the first automaton. Which means that we really have to get all the final states of the first automaton as well. Now, that's a little tricky, so don't write that down yet. This is what you probably think of having F alpha union F beta. But that's wrong. And it is wrong for the following reason. This would always contain Q0, because by definition F sub beta contains Q0 in that particular case. Now, when should the initial state of the concatenation automaton be accepting? That's, of course, equivalent to asking when can we have W be epsilon? Well, if we have epsilon written as the concatenation of two words, what can we immediately say about those two words?
They're empty.
They must both be epsilon. The only way you can write epsilon, the empty word, as the concatenation of two words is if both of those two words are epsilon. Now, if you look at this, this will always say epsilon is accepted by the concatenation construction, even though the initial state of the second automaton may not be accepting. So what we really need to do is we'll take F sub beta and take the Q0 away from it. So that then means that only Q0 will only be in F2 if both Q0 is in F beta, this is that case, and if Q0 is in F alpha. Okay. So only if both initial states are accepting, then we will have in Q0 in F2. So that defines F2. And finally we get to Q and A. And so there are three cases that we have to distinguish. Q, of course, is in Q2, and A is in little a. So where are things interesting in the transition function? Well, the only interesting case is the final state of the first automaton. So if Q, this Q, is in F alpha, that means Q is a final state in the first automaton. That implies that we obviously want to be able to do whatever we can do before, so that would be tau sub alpha of Q and A. That's all the stuff that one can do from that Q in the first automaton. And now we also want to add the functionality of the initial state of the second automaton. So we do union tau of sub beta, that's the second automaton, the transition function of the second automaton, of Q sub 0 and A. So that basically then encapsulates the idea that every final state of the first automaton, well, it will do whatever it did before, so that is that. But it also can act non-deterministically as an initial state for the second automaton, which is tau sub beta of Q sub 0 and A.
Professor, just in case if I missed it, right now we're going through tau, which is the transition function. That being said, we're applying tau of whichever state that we have in A, and then we're trying to, I mean, in alpha, and then we're trying to union it with the beginning of anywhere in Q.
But only if that state is a final state of the first automaton.
So once we stop counting in alpha, then we can begin on beta.
We can jump over into the second automaton, correct.
Have you mentioned anything about stopping anywhere? Or
Well, if you end up in a final state, you can stop and the word is accepted. If you don't, it's not accepted.
So the final state, does beta contain any final states?
Well, presumably, by assumption, there is f sub beta. The non-deterministic finite automaton n sub beta has the final states f sub beta, just like the n sub alpha has f sub alpha as final states. All right.
Lastly, the point of doing this is so that could you go over again what we're trying to accomplish here?
We're trying to construct an automaton that accepts the concatenation of whatever each of these two automata accepted.
Okay, got it.
So what we want is an automaton for the concatenation of alpha and beta. That's what we're driving at. No more and no less.
Okay, thank you.
Okay, and so the transition function, as I said, is interesting for final states of the first automaton. If we have a state that is a rejecting state in the first automaton, then we're not changing anything. So this is tau alpha of Q and A. Nothing new. Same old. Whatever we did before, we continue. And if we have a state in the second automaton, except for the initial state, because the initial state is basically covered in one of those two, then we're going to do exactly the same that we did before, except of course now we're in the second automaton. Other than that, so any state that we have here, we continue doing whatever we did before. So the only thing where anything new happens is the final states of the first automaton. So I don't have time to do the star construction, but I do want to do at least a very simple example of the concatenation construction. So let's do A concatenated with B union A. And let's assume the alphabet is AB. It could be more than that, but in this we do need A and B, but there could be other letters. But in this case, I'm assuming we only have A and B. So we need an automaton for A. So 0, 1, A and B. 0 under A goes to 1 and nowhere under B, and 1 under A and B goes nowhere, so this is the automaton for AB. For A, I'm sorry. And then we need an automaton for B. So here is an automaton. Now, the trick that we're going to use throughout is that we number these letters, 1, 2, 3. The initial state is always going to be 0, and the other state, if you look at the definition of the basis, we have an initial state, and then we have another state for the letter. Well, that other state then is always going to be the number of that letter. So this is the first letter, this is the second letter, This is the third letter, so we have 0 and 2. And so we have A and B, and under A from 0 we go nowhere, under B we go to 2, and then we have the same thing, R, 0, 1. And finally, the third letter, A, we have 0 and 3. And we have A and B. And 0 under A goes to 3, and under B goes nowhere, and 3 doesn't go anywhere, and 0, 1. So now we have the 3 automata for the basis, and now we can do the concatenation construction. Well, by definition, the states are 0, 1, 2. If you look at this, then you will see that they obviously are satisfying the non-returning property. You can't go back to the initial state because nowhere in these transitions do we have a 0 occurring. And so we do the union, these 0, 1 and 0, 2. The union is 0, 1, 2. The final states, well, where do we have to look? We have to look at the initial state of the second automaton. The initial state of the second automaton is rejecting, so we're looking at this case. So the final states of the concatenation of those two automata, therefore, is simply the set consisting of the final state of the second automaton, f sub beta, which is 2, and the other two states are rejecting. And so the initial state is, of course, 0. And now we have to do the transition. Well, where do we look? Well, we look at the first automaton. The initial state is rejecting, which means we're looking at this case, which means we're copy. When nothing happens, which is here and there, and the same thing for the union construction, nothing happens here, nothing happens there. This is simply copying. We copy whatever we have. So we take 0, 1. So 0 is 1 and nothing, because this is rejecting and there is nothing to be done. So this is this case. 1 is accepting, so we're looking at this case, okay, which means we take whatever we had from that state in the first automaton plus whatever we get from the initial state of the second automaton. So we have nothing, union nothing is nothing. Nothing union 2 is 2. And then in the second automaton, everything except for the initial state, of course, is only copy. So that is this. So this is now the construction of the concatenation of A, B. And if you look at this, well, you go from 0 under A to 1, from 1 under 2 to B, from 1 under B to 2, and 2 is accepting. So really AB is accepting. And then if we do the union construction of this resulting automaton and that one, we have 0, 1, 2, 3, A and B. Final states, according to the definition, is all the final states of the two automata. So that would be 2 and 3. What happened? Yeah. Are you disappeared on me? Come on. Where was this? Come on. Where do, yeah, I'm trying to, there's an undo. No, no, no.
There's no one to the left of that, like the arrow pointing like left. Yeah.
This one?
Yeah, that's the undo button. But you have to press cancel on that window in front of you real quick before you can press it.
Ah, thank you, thank you. All right. But what is that? I had 50 Control C. Okay. There. So I wanted to go back to this one. The union means we have the union of all the final states, which I just did. So this is A and B. And so the final states are final states of the first automaton and final states of the second automaton, so 2 and 3. And 0 and 1 are rejecting. And 0, of course, is the initial state. And now, going back to the definition, the only time when anything interesting is happening is if we do the initial state. And the initial state basically says we're doing the initial state of the first automaton union the initial state of the second automaton. So this is 1, 3. And nothing. And everything else, if you look at that definition, everything else is simply copy. Nothing new happens, and therefore we do this. And so this is 1 is nothing, 2. 2 is nothing, nothing. 3 is nothing, nothing. So this is now the automaton for A concatenated with B union A. And that gives you a little bit of an idea how this happens. Now, on Monday, we're going to do the star construction. We've done so far the union and the concatenation. The star is not that complicated. The most complicated one is the concatenation, but I don't have time to do that. I don't really want to run over. Any questions?
I have a couple of questions. No, the last one, can you go back to the last one?
Yep.
Awesome. So right here, the final automaton, it's kind of what's expected from us if you were to put A concatenation B union A, correct?
Yes.
And what is this doing? Once we get to this point, now we can actually say that we have the ability to go between any
What we
A
have
and
now is a finite automaton that accepts precisely the language that is denoted by this regular expression. So this regular expression defines a language. It denotes a language. Now, this is a very trivial one. It consists of 2 words, A, B, and A. And this automaton is also trivial. It accepts precisely those 2 words. So what we are going to show eventually, once we've done the third construction, is that given a regular expression, alpha, which defines the language else of alpha, we can construct a non-deterministic finite automaton n sub alpha that accepts a language. And that language happens to be exactly the language denoted by that regular expression. Now, when we do the converse, meaning constructing a regular expression for a given non-deterministic finite automaton, once we have done that, and that's the second step that eventually follows, then we have established that the two mechanisms, regular expressions and finite automata, are equivalent.
My next question is in terms of the exam. Do you happen to have any exams, prior exams for prior years that we can take a look at to study?
Exercise sets are a very good way for you to practice.
When is the exam?
Whenever it was announced, I don't.
February 22nd.
On the 22nd of February.
Okay, thank you.
Okay.
Is it possible that we could take a look at some previous exams, or is that not?
I just said the exercise sets are exactly what this is designed for.
Will the test be at the same time the classes?
Yes.
Okay, thank you.
Any other questions?
Could you go through all the slides so we can take a picture?
Absolutely. Slide 1. Slide 2. And slide 3. Now, if you don't follow some of the notation, the handout that is on the website, regular expression to NFAs, gives you all the details clearly, and you can, I would encourage you to download that and see exactly how that works. I mean, I'm explaining it, but probably it is easier readable on that handout than in my scribbling. Okay, anything else?
Is there a answer sheet for the exercise sets so that we can ensure that we
But you can ask me questions about it. See, these things you have to actually do. This is, my comparison is with riding a bicycle. I can ride a bicycle in front of you 1,000 times. You will not learn to ride a bicycle from that. You actually have to ride the bicycle yourself and fall off a couple of times. And so I'm not handing out answers, because the key is to be able to do it, not to actually look at what the answer is.
But if we don't have the answers, it's kind of like riding a bike in 0G and that we don't know if we fell down or not.
I'm showing you some examples, and when we do the regular expression to finite automata, I will give you some additional examples, and that will involve some of the things that some of the constructions. At this point, you really have only one or two constructions. You have the construction of a deterministic finite automaton from a non-deterministic finite automaton, and you have a partial construction, because I haven't given you the star construction yet, of a non-deterministic finite automaton from a given regular expression. So if you don't have any star, then at this point you could actually do all of that. But obviously we need the star construction in order to do all of the regular expressions in general. So I will give you examples. I just won't give you the answers to the exercise sheets, but I'm perfectly happy to answer questions about them.
Is there any way for us to check our work in automatons?
I think what they're all asking basically is if you give us like the answers, then
I am not
it
going to
kind of
give you
shows us
answers.
the best way
I'm
to do
sorry,
something.
I will not give you the answers because that means you're not going to do it.
If we finish it, will you give can we like send it to you and check to make sure that we've done it so we can know that we've done it correctly?
Professor Lace, I remember you saying that you wouldn't give us the answers because there's no right answers. Sometimes there could be
In
multiple.
some cases, there are more than one answer. So just because your answer isn't exactly the same that I'm giving you doesn't mean it is wrong.
But
But
would
if
you say there'd be like the most efficient answer? And I think that's what we're looking for instead of
the most
bad habits.
efficient answer is you simply follow the algorithms that I give you in class.
Okay.
And we will do examples, so don't panic yet.
All right.
Right, it's just I don't want the first time to I find out that I'm doing it wrong be when I get it wrong on the exam.
Yep.
I will give you examples and you will be able to see what you're doing right and what you're doing wrong.
Okay, thank you very much.
Okay. Anything else? All right, then I will see you or talk to you on Monday.
Thank you, Professor.
Bye-bye.
Adios.